The same thing happens here, right? So you can say the derivative becomes a delta function, but then what does it mean? And here is what it means. So there are weaker forms of differential equation, right? So this form we have been looking at is called the primitive form. And from the primitive form, you can derive two forms. One is conservative form, and one is integral form. And only in the integral form, the differential equation is going to make sense, even if it has a discontinuity. But in order to derive the integral form, you have to go from the primitive form and then into the conservative form, and from the conservative form to the integral form. So here is how it works. So first of all, I'd like to say that not all differential equations can be converted into an integral form. Only a particular type of equations can. And actually, this kind of nonlinear hyperbolic equations always can be converted into conservative forms. A conservative form is something that looks like this. Partial w, partial t, plus partial f of w, partial x, is equal to 0. Okay, so what's the difference? The difference is I'm not taking a derivative to w anymore. I'm taking derivative to a function of w. That function of w is called flux. Okay, and why it's called flux is going to be pretty obvious after we convert it into integral form. And the reason we can convert that into integral form is that there is nothing multiplied on the spatial derivative. So if there is nothing multiplied by the spatial derivative, we can actually integrate over space to get rid of the spatial derivative, right? So if you integrate the primitive form over space, actually it becomes not obvious what you can do. But if you integrate the derivative of f over space, well, the derivative goes away, right? And if the derivative to x goes away, it doesn't matter if the function is discontinuous in x or not. So that's the idea. Okay, so for example, how do you convert this black equation, the Burgers equation, into conservative form? Yeah, the derivative of w squared is actually equal to 2w times w, times the derivative of w, right? So w times the derivative of w is just equal to half of w squared differentiated to x. So an example would be this plus, well, I'll just write down what f is. The example above is fw equal to actually w squared over 2, right? Is it clear? Okay, good. So now how do we go from the conservative form to the integral form? We just integrate over an arbitrary region in space. So integrate over any interval a to b. And in multiple dimensions, it's really integrating over an arbitrary volume, right? If it's 3 dimensions. And this is actually where the name of finite volume comes from. So if the differential equation is satisfied over any point, then integrating that 0 over any interval or volume is also going to be 0. So, okay, so now let's simplify this. The integral of time derivative is actually just equal to the derivative of the time integral, of the spatial integral, right? So because one integration is in space, the other integration is in, the derivative is in time, that makes it commutable, right? So plus now, what is the integral of spatial derivative? I'll just write it fw at a and b, right? So this denotes the fw at x equal to b minus fw at x equal to a, right? So that's the integral form. All right. So if you write down the integral form of the Burgers equation. It'll be d dt of integration over any a to b wx plus, well, w b squared over 2 minus wa squared over 2. Right? So that's the integral form of the Burgers equation. Okay, so now you can see that this actually only has time derivative. It doesn't have any spatial derivative, right? So even if the function w, the solution w, is discontinuous in x, it has shockwaves, it doesn't matter. Okay, this equation still makes perfect sense. And in addition, this equation is actually going to be used to analyze how a discontinuity is going to behave. So, for example, imagine I have a discontinuity that's actually symmetric. So I have a discontinuity. So let's say on the left of the discontinuity, the solution is w equal to 1. On the right hand side of the discontinuity, w equal to minus 1. Okay? Can somebody use the integral form to tell me how is the discontinuity, in which direction is the shock wave going to move? Towards the right? Why? Okay, so what you said is because this integral cancels out, right? So if w is either equal to 1 or minus 1 with no intermediate values, what it means is that for whatever x, w squared over 2, the flux is going to be equal to what? Half, right? So if you draw the function of the flux, it'll be a constant. So if you take any interval a and b, what is wb squared over 2 minus wa squared over 2? It's 0, right? So now over any interval a and b, what is the derivative in time of the integral of the integrated w over that interval? 0, right? So basically that means if you look at any interval, the total w in that interval would never change. What does that mean? That means nothing changes, right? I mean, if the shock wave actually moves one side or another, then the interval, if you take an interval around the shock wave, then the interval is going to change. I mean, the integral over the interval is going to change, right? If it's moving towards the right, the integral integrated around the shock wave is going to increase if it moves towards the right, right? If it moves towards the left, the integral over the shock wave is going to decrease, right? Either way, it's impossible to have d dt of integral from a to b to be 0. So the only possible solution is that nothing changes. Okay? Well, I mean, there is a caveat I'll tell you later on. So nothing changes provided that the discontinuity stays a discontinuity, right? If you are allowed to actually make it have this smoothing out, actually the same equation actually could be satisfied without with actually some changes. So I'll show you that later. Okay, so this is one behavior of the shock wave that we can that shows that we can analyze the behavior of the shock wave from the integral form of the differential equation.